Hello, welcome to a new video on topological spaces. In this video, we define the concept of relatively closed sets. After defining the relatively closed sets, we will state and prove a result on relatively closed sets. After completing that, we will prove that some properties are hereditary and some other properties are not hereditary. So let's see what's I mean by a relatively closed sets. For defining relatively closed sets, we need a topological space. See, let X be the original topological space, and then we consider a subspace of that original topological space. Subspace is A. Then we know that for that subspace we can define, or we can find a relative topology, a subspace topology we can define that is related to the original topology. So we can define a subspace topology for A. So there exists a subspace topology for A, but that subspace topology is related to the real topology, original topology, which exists or which makes the space X a topological space. We consider a subset D of the subspace A. Let D be a subset of the subspace A, and we can say that it's a relatively closed set. If it is closed, if that subset is closed in the subspace topology of A, so which exists, that subspace topology which exists in A, related to that subspace, if we can treat D as a closed set, then we say that it's relatively closed. So D is relatively closed. More clearly, we can say that D is relatively closed if and only if A minus D. A minus D is the set obtained by removing all points of D from A. So if and only if A minus D equals O intersection A for some open set O in X. See, here O is an open set in X. So for that open if there exists at least one open set in X, such that A minus D equal to A minus D equal to O intersection A. See, we know that D has the properties of a closed set. So when D is removed from the subspace A, then you can think that it is it's an open set. It must behave like an open set. So for making it an open set, see, there must exist an open set in the original space X. So that's why we define it in this way. So there must exist an open set in X such that its intersection with the subspace A equals A minus D. Okay, now coming to that the result, we consider here a subspace of, you see, there exists a topological space X be the original topological space, then its subspace is taken A, and its relative topology or the subspace topology, see, is also taken prime B the subspace topology. So we pair them A comma tau prime. A comma tau prime is now a topological space. It's a subspace of the original space X. Okay, then the subset D of A is closed. See, actually we are going to state the theorem about the subset or closed subset of the subspace. So let us consider D be D as a subset of A. Then it is closed if and only if if and only if there exists C, there exists a subset C, that must be closed. A subset of X. It must be a closed subset of X such that D equal to C intersection A. So actually the statement is a subset D of A is closed. Subset D of A is closed in the subspace topology for A. In the subspace topology for A, if and only if D equal to C intersection A for some closed subset C of X. See, here we want to show this, we want to prove the statement in both directions. So suppose first we suppose that D is a relatively closed set. Then we know that by the definition of a relatively closed set, then we know that A minus D equal to O intersection A for some open set O in X. See that definition which is stated above. So there must exist an open set O in X such that O minus D equal to O intersection A. A minus D equal to O intersection A. And then here D, therefore we can write D equal to then A minus D. It's very clear. So we can write D equal to A minus D. So it's because two times we are separating, we are applying that subtraction. So so this is like taking complement of complement, and it's an operation like that. So A minus D. Then we know that a complement, the whole complement equal to A. Like it's similar to that. This expression is written. So D equal to A minus D. And then this is now we can we can write it as A minus O intersection A. Why? Because A minus D, we know that A minus D equal to O intersection A. Here we have that. So it's substituted here. So A minus O minus O intersection A. A minus O intersection A, and that equal to, that can be written equal to X minus O intersection A. So this becomes X minus 1. Here we are bringing that or applying that whole space. We are using the whole space here. So by using whole space, by removing from the whole space that open set, and then taking. So first we remove that remove the open set from the whole space. Then no part of O is there present in this set. Then after that we take its intersection, the new intersection of this new set with A. So X minus O intersection A will be then equal to A minus O intersection. Here we take O intersection A. That means only those part of O which are contained in A are here taken, and then that is removed from A. So this becomes, now you can see that it's equal to X minus O intersection A. Okay, and so D is the intersection of see here, D is the intersection of A with the closed set C equal to X minus O. So here X minus O is clearly, because O is, since O is an open set, X minus O is a closed set. That's very clear. So since X minus O is a closed set, then a closed set intersection C, it's in the intersection A, and therefore D is D is the intersection of A with a closed set. Thus we get that the proof, the complete proof in one direction. Therefore D is the intersection, what we get here, D is the intersection of A with a closed set. That closed set is C equal to X minus O in X. Okay, next to prove the conveys, the reverse implication, we suppose that here D equal to C intersection A, where C is some closed set in X. We take, or we suppose that D equal to C intersection A, where C is a closed set in X. then since C is closed in X, if we subtract C from X, we get an open set, and that set is taken here equal to O. So O is equal to X minus C is open in X. And now you can think about A minus D. Then A minus D equal to A minus what is D? D equal to C intersection A. That can be used to substitute. So A minus D part is replaced by C intersection A. Here C intersection A is is substituted. Then again applying that the simplification step that we used in this previous simplification that we used in this previous step, the same thing we can apply here. So A minus C intersection A, that can be written as X minus C. See, this can be written as X minus C. See, X minus C intersection A. But X minus C, we know that X minus C equal to O, an open set. So we can substitute that here, O intersection A. And hence we get that A minus D is open is open in the subspace topology of A. See, A minus D, therefore A minus D is, since we get that A minus D equal to O intersection A, and thus A minus D is open. So A minus D is open in the subspace topology of A, and D is therefore D is a relatively closed set. So since A minus D is open in the subspace topology of A, we get that D is a relatively closed set. Next, we now define the hereditary property of topological spaces, which are called hereditary property. What is meant by hereditary property? So we are now talking about spaces and their subspaces. Okay. Now, suppose a space has some property. See, think about all subspaces of that space having that the same property, and that kind of property is called a hereditary property. See, it's because if a mother has that property, so a mother has a property, and suppose all her children have the same property, then we can say that it's a hereditary property. So in a similar way here, the mother here the original space acts as the topological space. Original topological space acts as the mother, and its subspaces can be treated as its children. So when the mother has a property, if all her children have the same property always, then we say that that property is called a hereditary property. So, but how can we define it? Using in mathematical terms. See, a property P of a topological space is called hereditary. Provided that if X has that property, if X has the property P, then every subspace of X has the same property. See, if X has if X has the property P, then every subspace of X has the same property P. Now we see some examples. We discuss some examples of hereditary properties. See, first of all, see, first countability and second countability are hereditary properties. See, first countability, repeat. First countability and second countability are hereditary properties. So how can we show that? If X, or how can we justify that? See, if X has a countable, so for that let's first consider to prove that first countability is a hereditary property. So for that we consider a topological space, an original topological space like X, and suppose X has a countable local basis Bn, where n varies from 1 to infinity at a point at a point A, where A is an arbitrary point of X. See, suppose that So for that, suppose x has a countable local basis Bn, where n varies from 1 to infinity, Bn, or b1, b2, b3, etc. It varies going up to infinity, b infinity. At the point a is the fixed point in x, and let a be a subset of, and we consider, after stating this, we consider a subspace a of x. Let a be a subspace of x, and that also contains x, contains a. See that a is the fixed point in x, so a fixed point in or a particular point in x, and then the same point may be there, it must be present in the subspace also, and then only we can define this. See, therefore, thus we assume that a is present in a also, in the subspace also. Then we can, by taking the intersection of all the members of the local basis. This is the local basis. You can then what are the members b1, b2, b3, etc. are the members of this local basis, and we can take their intersection with the subspace A, and we can obtain another collection, a new collection. That collection contains b1 intersection A, first element, and b2 intersection A, the second element, b3 intersection A, the third element. And in general, we can as a short form, we can write it as Bn intersection A, the collection Bn intersection A, as n varies from 1 to infinity. See, then after defining this, we can see that we can show that it's a local basis, and this collection acts as a local basis at the point A in the subspace topology of A. So this is the thing that we want to show. Actually, if we can show that this new collection is a local basis at the point A in the subspace topology of A, we are done. Okay, then it's very simple actually to show that. Then this is the we want. We want to define or we want to obtain a new collection, and this new collection is obtained by using this the intersection of the open intersection of the members of the local basis. Bn is the local basis here, which is given provided here as the local basis for the point A in X. Then its intersection by taking the intersection of all the elements of that local basis with A, and we get the new collection. That new collection can act as the local basis for the point A in the subspace topology of A. So there is no need to prove it further. It's very simple thing actually to understand that. Next, to show that the second countability is also a hereditary property. So for that second countability, what's meant by second countability? A topological space is said to be second countable if it has if it has a countable basis. So since it is given that X is, or we take X the whole space as second countable, we treat X as second countable, then there must exist a countable basis Bn. Let Bn, where n varies from 1 to infinity, is a countable basis of X. We take that, and in a similar way that we have defined in a new collection, here also we can define a new collection by taking the members of taking the intersection of the members of that countable collection with the subspace A. Thus we get Bn, the collection Bn intersection A as n varies from 1 to infinity. We can in this case also we can verify that it acts as a countable basis for the subspace A. So this is also a symbol. So by the rest thing is not done here. So we can verify that. Next, we will show that a property is not a hereditary property. That property is separability. See, separability in the case of topological space is not hereditary, so you should. I repeat that. So separability is not a hereditary property, and that what does it mean? There can exist a topological space X that is separable, but that has at the same time it has a subspace which is not separable. See, yeah, that so in order to prove that separability is not a hereditary property, it is it's just a matter of giving an example to show that there exists a topological space having this property. So for that, for that as an example, see, consider the subspace X of R2. Or the subset X of R2. R2 is the Euclidean two-dimensional space. See, R2 consisting of the real axis R. So for that we consider the real axis, see, X and Y axis, and then the real axis, that is X axis, is taken here. In R2 we consider the X axis, the real axis R, and one additional point. That additional point A equal to 0, 1. 0, 1 is the point 0, 1. The additional point 0, 1. That point is the point lying on the y-axis, right? Yeah, it's a point on the y-axis, and which is at a distance of which lies at a distance of 1 unit at the top above that line, real line that we consider here. The real axis, above the real axis at a distance of 1 unit away from that line. This is the point. The point A equal to 0, 1 is taken. So this is the now the subspace is taken equal to the union of the real line and this point. We define we need a topology, a relative topology, subspace topology. So we define a topology on X. So first of all we need the topology on X. Which consists of the empty set phi and all the subsets of X which contain A. See, how do we define the topology? First, we define a topology on X. On X that consists of the topology consists of the empty set phi and all the subsets of X. See, we also consider all the subsets of X which contain the point A. Then X2 is a separable. Then X2 is separable, and in this with respect to this topology, X2 is separable since the singleton set set A is dense. Then okay, since the singleton set A is dense. Then the topology X2 is the space is then a separable space. But the subspace topology, in the subspace topology top prime, we also consider the subspace topology top prime for R when that subset is treated as a subspace. As the subspace of X is the discrete topology. See, since we here we take the we consider, for example, the subset here. X is taken as the subset of R2. See, the origin space is R2, and X is the subset. So on this subspace. In the subspace topology, that subspace topology is related to the original topology which is defined here. You can see that it's a discrete topology. The subspace topology is a discrete topology, and so R top prime is not. See, therefore X top prime is not separable. So there's a correction. See, X top prime, because top prime is the subspace topology. Therefore X top prime is not separable. It's not R top prime, X top prime. That's the subspace we have to state. So it's not separable. Yeah, that's the example which states that the separability is not a hereditary property. Okay, thank you.